Hi and welcome to Lab 1, Constant Velocity of Motion using the Principle of Momentum or Newton's second law. In this lab we are going to perform an experiment which consists of rolling a tennis ball at a constant velocity. We are going to build a computer model and compare our experimental results with the model results. Let us begin. Momentum P is defined as a mass times velocity. Next we have the principle of momentum, which is the change in momentum is equal to the sum of all forces F net times delta t, where delta t is a small change in time. We rewrite delta p as p final minus pi. Next we set delta t to F net times delta t and solve for pf. We now have our update prediction formula for momentum pf. This allows us to make predictions into the future based on prior information pi, F net, and delta t. Replacing p with m times v in this equation, and then further dividing through by the mass, we get the velocity update formula. Finally, recall the position update formula. Rf is equal to Ri minus the average velocity times delta t. V0 and m have both been estimated. But what about F net? In order to have constant velocity, F net needs to be equal to 0. If we have a look at the velocity update formula at the top of the slide, we see that if F net is equal to 0, then Vf is always equal to Vi. In addition, the mass of the object is also removed. As a result, the mass of the object does not affect the velocity. In other words, the mass does not matter. Here we have a tennis ball and the floor. The tennis ball is taken as our system, which will be acted on by the surrounding around it. For example, the floor and everything else. Using a free body diagram, we see that the only force acting on the tennis ball are the force of gravity and the force of the floor, which acts equally to the magnitude of the force of gravity. In addition, we are ignoring friction. Summing all the forces results in F net equal to 0. We are ready to start modeling. We have imported our experiment video into Tractor, setting up our axes so the tennis ball moves in the left direction or in the negative x direction. On the floor we see a ruler used for the purpose of calibration. The ruler measures 0.3 meters. It should be noted that the y variable changes slightly throughout the video. This is because when setting the point mass, it is not always at the same y position. In addition, note that at time 0, y is equal to 0.018. A way to set this equal to 0 is to have the axis align with the center of the ball in the y direction. I chose to ignore the y component since we are modeling 1D motion. Here we have the radius of the ball being 0.03, the mass of the ball being 0.059. Recall that the mass is actually negligible in the constant velocity case. We've set the ball's position vector or initial position to be the following, and the ball's initial velocity to be the following. We start time at equal to 0. The delta t is equal to 0.01, and we run the loop up until 0.733. Here the velocity update function has been implemented, as well as the velocity position function has been implemented, and we are set to run the code. Looks pretty good. Here is the result. The experimental data is plotted in blue, while the computer model is plotted in red. We should note that both plots don't start at 0, 0. This makes sense since the initial displacement did not start at 0. It seems like the model is performing relatively well when compared to the experimental data. However, we should note that the time period over which the experiment was done is very short. This was done to capture the constant velocity. As time would progress, we would expect the predictions to become less accurate. We can see towards the end that the model is starting to steer away from the actual experimental data. If we were to extend the period, I would expect the line to separate from the experimental data, which would eventually flatline. Reasons for this is due to assuming that F net is equal to 0, or there is no friction. If we were to repeat rolling a ball along a floor, eventually the ball will come to a rest, and this is due to the forces acting in the surroundings onto the system. Here I've made an orientation change on my axis. However, my results to the right have not changed. My data has changed. So if I were to actually plot this my object would be going down on the y is equal to minus x line, approximately. However, my data hasn't changed with respect to the velocity. In this example, we assume that the net force is equal to 0. Therefore, we are assuming that there is no friction. However, the forces that are acting upon our system is the force of gravity and the force from the floor. The force of gravity pushes downwards, and the force of the floor pushes upwards at an equal magnitude. As a result, both forces cancel, and therefore our net force is equal to 0. Thank you for watching.